Okay, so hi everyone, I'm Chris Saxon. I'm part of Stephen Feuerstein's Oracle Developer Advocate team. It's my job to help you get the best out of Oracle Database and hopefully have some fun whilst doing so. So in that mind, we've got some interesting questions come in. We had on regular Ask Tom, people ask some tough SQL questions, and I looked at them and I thought, actually, it'd be interesting to get some help from the community on answering these. So I reached out on Twitter towards the end of last week, to see if people could help me, and the community didn't disappoint. Lots of people helped. However, something was pointed out in these that maybe SQL may not be the ideal solution for these problems. So with that, I've also got Hans, who's PM for Graph and Spatial as well. He's going to talk a bit about how these might be graph problems. Can I say hello, Hans, quickly?
Hi, Chris. Thanks for having me.
Yeah, no worries. Okay, so we'll start off. We've got a couple of problems, and the first one is a graph traversal, or graph traversal type problem. So we've got a graph that looks like this. So we've got a number of vertices, that's all these points A, B, C, and D, and so on, and edges between them that connect these. And what the person asking the question wanted to do is find all the fully connected subgraphs. So that means every graph where every vertex has an edge to every other vertex within it. So if we look at our graph here, we can see, if we look at, say, A, B, and D, we can say that is a fully connected subgraph, because A is connected to B, B is connected to D, and D is connected back to the A. So all of them are each point is connected to every other single point. If we look at another little group here, so we've got, say, A, C, and F, so we look at those. This is not a fully connected subgraph. There is a path between them. We can get from A to F going via C, but there is no edge back from F to A, so it's not fully connected. So we wanted to split this graph up into all its fully connected subgraphs, all the subcomponents within it, which gives a list that looks a little bit like this. Now, the interesting thing is, when the person who asked this question actually only gave a subset of these subgraphs, and I didn't check closely enough that they included everything, so I announced this problem, and quite a few people were quick to point out that, hang on, haven't you missed a couple of things here? And it's like, oh yes, I have. And you can see we've only got 6 vertices here. So you can see that actually very quickly becomes tricky to visually inspect and see that you really have got all the fully connected subgraphs. So, you know, quite often when you're doing something, it's good to have a visual double check. It becomes very quickly hard to do this when you're doing these subgraphs, particularly if you've got a lot of connections going on here. So that's what we're trying to do. So how can we solve it? Well, there's a few kind of techniques we can use. But before we do that, there's some simplifying assumptions which make things a lot easier here. First up, we're going to say that the edges are bidirectional. That means if A is connected to B, that means also B is connected to A. So you can go both directions on each edge. This makes solving this a lot easier, because if they are directional, we say A is connected to B, but we also have a link back from B to A to say it's fully connected. We got to essentially double up the work that we're doing. So making sure that they are bidirectional makes this a lot easier. Some people might wonder what's bidirectional versus directed. If you think something like Twitter, you've got the follows relationship. I might follow you, but you may not follow me. So it has direction whether or not you are following someone. You can follow someone who doesn't follow you back, and vice versa. Whereas in something like Facebook, the friends relationship is kind of bidirectional. By agreeing to be friends, you've both agreed to that. So some relationships are bidirectional and some aren't. For this, we're going to say they're bidirectional. Also, again, we're just going to say that each edge only appears once in the data set. This is probably something that should happen anyway, but just, again, makes things a lot easier. And in terms of how we're storing it, we're saying that the lowest vertex is stored first. So, and that is just how you sort them. So if we've got a relationship, an edge between A and B, we store it as AB, not be A, because A appears before B. That makes some of the solutions that we've got a lot easier to do, because then we can rely on the fact that we've got that order in how the entries appear. So we've made some simplifying assumptions. Then how can we go about actually solving it? Well, one basic technique is we can look at start generating possible subgraphs. So we'll start following the edges around and seeing whether or not they actually form a fully connected subgraph. And we'll see various solutions to this. We can take like a very naive solution and just say, generate every single possible subgraph within the graph we've got, or we can be a bit more targeted and say, only add things which actually have some connection back to one of the original vertices we've got. Having generated our set of possible subgraphs, we then can join it back to our original relations table, which stores all our edges. So we'll have a subgraph which might be A, B, D, and then we'll join it back to the rows in the relations table. And if it is fully connected, then the number of edges or the number of rows will be the sum of 1 to the number of vertices, which in basic maths formula is the n squared plus n over 2. So that's how many edges we want to check. So once we've found a particular subgraph, we then say, is the number of edges equal to the number of vertices times the number of vertices plus 1 divided by 2. So that's this formula at the bottom, and we'll see some of the solutions in SQL take advantage of this. Okay, so at this point, we had quite a few good solutions come in from quite a few people, so I was going to jump over to Live SQL and start looking at some of them. While I bring that up, does anyone got any questions or comments at this point? Anything they want to say? If you just pop it in chat, if you let us know. If you're struggling to follow along at all, again, just let us know. It can be a bit tricky to fully understand exactly what's going on here. I know when I first read the problem, it took me a few minutes to get my head around it. So, if you need us to stop and take a minute, just let us know. Okay. So I'm not seeing any questions, so let's just kind of look down. So we've set up our table. So primary key, each edge only appears once, and making sure that they appear in a particular way, and we're storing the data in. And as I said, these are the relations that we want to look for. Now, I'm going to walk through a few basic solutions. I'll make this a little bit bigger, so a bit easier to see. Now, one of the first solutions we had was something that came in from Oren, and that was just to generate every single possible subgraph within that is in it. So link every vertex to every other one, create an edge for it, and then check whether the edges, those edges genuinely exist. And he does this by using collections. So we can build up this collection, our Oracle nested table, and then we can have this thing called a power multiset, which automatically just does that explosion for us. It looks at every element within it and then generates it combined with every other element. So we get a massive explosion of our data. And the cardinality as well is a neat built-in, which tells us how many elements there are in that set. So we know how many vertices there are. Then if we go down a bit, we can take advantage of some of the member functions. If we look at our relations, are both vertices members of this graph that we've just generated? So we're saying we've got our graph A, C, F, and how many of those relations, so we check the relations in the table for the edges, so we're looking for AC, CF, and AF. Are they all in that table? And that's where this bit comes in. And then remember we had that formula, sum of 1 to n elements. That's what we're doing down here at the bottom. Now notice we've also got this check that there's at least 3 vertices in the subgraph. It's worth kind of briefly mentioning that, of course, each pair is itself a fully connected subgraph, because A is connected to B, B is connected to A, so it's fully connected. But it's actually not that interesting in this example, because they're bidirectional, That's just the data we have in the table. So for completeness, in theory, we probably should include that, but it's just not actually that interesting in this example because that is our original data set. If you needed it, you could union it on or add it as part of your filtering or not filter those out. So it's worth mentioning that if you need the true fully connected subgraphs. And as you can see, obviously, from the fact that Live SQL doesn't support this, we've got all our subgraphs. So this is a neat solution. It shows you how to use these set functions or the functions on these nested tables. But as you'll probably see, some tools such as Live SQL don't support these, or it's not fully easy to actually see what's going on here. Any questions or comments? Anything? I see you're on the call, Oren. Anything you want to add before as we move on? No? Okay. So next solution we'll look at very quickly is something that came in from Stu Ashton, and he approached this in another way and said, let's try and build up a tree. So a tree is just a form of graph, really. So we can use our connect by prior to connect every node with the other nodes. Now, one of the difference, what's going on here compared to the power multiset, is we're actually only building up possible subgraphs. So if I'll bring back my slide very quickly. If we look back here, we can see there is no connection from A to F here. Generating the power multiset would generate an edge from A to F and say, then check whether or not it's part of a fully connected subgraph. But we already know there is no connection there. So any subgraph that includes A and F, an edge between those, is impossible. So it's just not worth even including that in the first place. So that's where this optimization comes in. It only considers subgraphs which are actually true subgraphs of what we've already got. We don't include every possible thing which could possibly exist. And it goes through and builds up this little neat trick of little percent wildcards. And we're going, why does it do that? Why do you get all those little percentages on there? Well, what this allows us to do is use the like operator to see whether or not the pair that we want looking for is in this path. So you can see we've got, percent, colon percent. We can then easily check if AB is within the group that we wanted. So it's a neat little trick that Stu discovered, making this a bit easier to solve without having to use the kind of set operators that we had before. And as before, we had to do the check. Are the number of edges we've got here equal to the sum of the number of vertices in the graph? And here now we can actually see the solution we were looking for. So we've got ABC, ABCD, and so on. So we've got all our various different solutions here. I see you've joined us as well, Stu. So that was one of the first things came up with. Now, this is much better, or potentially a lot better than generating the power multiset of everything, in that we only consider possible subgraphs. However, we could still do quite a bit better. Something that I came up with shortly after Stu posted this was to check each node when we're adding it, does it have a link back to the root in the graph? So if we're going A, B, D, C, E, and so on, if we get to E, does that have a link back to A? If it doesn't, well, it definitely can't form a fully connected subgraph. So I added this little existence check in here, which helps reduce the data set complexity. But Stu was actually able to go a little bit further. And as we're building up this graph, we're walking through the tree, although not necessarily a tree. Is this relation part of a fully connected subgraph? So we're adding a new vertex. Is every link from that vertex back to the existing ones in the subgraph we have so far, do they all exist? If they don't exist, then we've got a problem and we want to discard it. And optimizations like this are actually going to become quite important, as we'll discuss a little bit later. So, Stu, anything you want to add on that, as I see you're on the call? If you're happy to chat, let us know. We can unmute you. Otherwise, just let us know in chat. Type it in the chat. So we've had a few solutions here come in, and then about 5 minutes ago, we had something come in from Sven Voller, and we'll bring this over. And he approached this in actually, as far as I can tell, a completely different way. And if I've understood this correctly, Sven, I've only had time to look this over quickly, so if you're able to chat through it, that would be better. He's built an API for managing this graph, and the way I understand it is every time we add a node to the graph, we're checking whether it's forms a fully connected subcomponent. So instead of storing our graph and then doing the computation afterwards, every time we change the graph, add or remove a vertex, say, well, does this form a fully connected subgraph? Does this form a new fully connected subgraph? And of course, the advantage of doing this on write, as we write the data to the database, is that we then have a table, which somewhere, maybe we can find it, we can just query. So then it's as simple as just querying the table. So this can be a good way of changing the processing. Some things can be computationally quite slow. If you can change when you do the computation to when you're storing the data as opposed to when you're querying the data, can become much more efficient to then get the result. Downside is, of course, you're moving that complexity to when you change to your writes. So you've got to analyze your trade-offs. Which is more important to you, getting data into your system quickly or getting it back out quickly? So comments from Sven, yes, main goal was how to make it fast. And the trick is to move the computation time from select to insert. It comes at a heavy cost. Yes, so it's a great point there. Anything else you want to say on that, Sven? Are you able to chat to us at all properly, or if not? So just so you know, these solutions, or the solutions I had at the time we went live, I haven't included Sven's yet, they are in live SQL, so if you want to just search for Ask Tom office hours, you can go through, pick them apart. It's probably one of those things, if you want to understand them properly, you do need to sit down and walk through the code and think about how they all work individually. So that's good. Good to follow that. Okay, thanks, Stu. Yeah, just to say the explanation was fine. So to reiterate, to kind of understand these properly, you probably need to work through them individually. I think it really helps to break it down, you know, even to just a 3 or 4 vertex graph, maybe a 4 vertex graph, walk through what the solutions are and understand how they all fit together. It just really helps cement how it comes together. Okay, another comment from Sven. The solution at the moment means only one session is allowed to insert and modify the relations table. The other sessions will, yeah. I didn't notice that, Sven. You had a nice lock table and exclusive mode somewhere in this API. So there's probably, yeah, there we go. Lock table and exclusive mode. So yeah, if you've only got one writer, this might be okay. I'm sure we could probably find a way to do this that doesn't require locking of the whole table, and maybe an interesting challenge for someone who's watching or to see if they can find a way to have this on write change work through it. But I like this because it's another way of approaching the problem. So it shows that sometimes if you change how the problem works, you can come up with different or better solutions. Okay, so Visconti, how would we test scaling for these? Just keep generating higher order names so we could have larger data sets? We'd have to know the solution was correct before testing. So that's a great question, Visconti. And with something like this, it's absolutely key that you start with a really small data set where you can actually, where you know what the answer is supposed to be, and then start fiddling around with it. Try adding and removing a few edges and see how does that affect results. So once you've got it working and you're sure then as you add more vertices and add or remove more edges, you're still getting the correct answer. Then you can start scaling it up and looking how it works from then on. And this is a great question, but the scaling question is a great one. And if I go back to the slides quickly, there is a general problem with this question, or solving this problem. It could be very, very slow. So if you're familiar with big O notation, we are talking 2 to the n. So what that means is if we've just got 10 vertices, there are over 1,000 possible subgraphs. If we go to a fairly trivial data set with 100 rows, so that's 100 vertices, there's something like 1 with 30 zeros after it. So 1 followed by 30 zeros is the number of possible subgraphs. Now, of course, in the real world, your data is probably not going to get anywhere near that number, but not anywhere near that number probably still means millions or billions of subgraphs, and that's on a fairly small graph with just 100, maybe a few hundred vertices in it. If we're talking, you wanted to do Twitter analysis or something like that, where there's thousands or millions of people, this is going to get quite slow, quite very, very quickly. So on this point, I wanted to bring up this comment from Babak. He saw my tweet and he was saying he felt that SQL isn't the right tool for answering. He felt that this is a graph problem. I mean, it's kind of in the problem statement, find the fully connected subgraphs. Sounds like a graph problem, right? So with that in mind, I thought I brought Hans on this to get his input and his thoughts on this, because I know you've got a take on this problem. So take it away, Hans.
Yes, okay. And maybe a quick comment up front. I was on leave until yesterday, and which means I was basically also refraining from using Twitter at all. And then this whole thing kind of, well, I wouldn't say exploded, but Babak raised it, and this whole thing evolved from there, which meant that I thought, okay, I'll have a look at that and have my colleagues look into it and so on in the few hours which we still have until you actually run this webcast. So, and just so that everybody's aware, Chris and I, we only agreed this morning that we would run the webcast together. This is kind of an ad hoc thing. So thanks again for the opportunity, Chris. So yes, as you were just saying, it is a typical graph type of problem, and we have a solution for it. In that we have had graph capabilities in the Oracle database for a long time. Not sure if everybody's aware of that. There is the Oracle Spatial Graph option for the Database Enterprise Edition, or if you want to use the cloud services, it's with the high performance or extreme performance edition, or included in the Exadata cloud services. We have had graph capabilities already back in 10G release 1, but those were purpose-built graphs. Now, for these kinds of problems, the one like with the subgraphs, you would want to use a sort of completely generic implementation of graphs, which is also known as property graph implementation. That's something which we have included in the database as of version 12.2. Now, when I say we've included that in the database, that basically means it is licensed with the database, and it uses the database to persist the graph. In fact, we would have 2 tables, one for the vertices, one for the edges, but we don't do a whole lot of processing down in the database. There's a few things, there's a few algorithms we can even run in the database. We have a converter that allows you to do pattern matching against graphs in the database using SQL. But for any kind of serious analytics, what you would want to do is use the in-memory analytics engine that comes with the product, which runs outside of the database, which has specific storage structures to actually do the serious analysis. And when I say serious analysis, that's basically 2 things. It can be either computational graph analysis using graph algorithms, or graph pattern matching. And we'll come to that in just a moment. If you want to move to the next slide, Chris. Right, just so that everybody understands what the architecture looks like. The Oracle Spatial Graph offering on the database means we have a storage layer, as I said, down in the database, and an in-memory analytics engine, which basically either works on a subgraph, which we extract from the database, or usually folks really load the complete graph into the in-memory data structures and run analytics there. When I say run analytics, that means that we would use scripting or Java APIs or the language bindings we have, like with R or the Spark integration and so forth, to actually do the analysis. Right? This is just so that everybody understands what this looks like. It is not plain database. It uses the database. It is nicely integrated with the database, meaning you can leave your data, like your tables, in the database, but the serious processing occurs outside of the database, which makes sense if you think about how these graph algorithms work or how the graph pattern matching works. You need to traverse the graph many times, usually, for certain types of algorithms. And that we can do pretty effectively in the analytics engine. Now, there's a comment from Dennis. It is not quite about SQL. Yes. Well, it's so I mean, anything could be not a right tool for these kinds of issues. Well, I mean, the SQL solutions we just saw are actually pretty impressive from my perspective. I mean, like Oren's solution is relatively compact, and it's always a question of, do I have a SQL-based environment anyway? In which case, it only makes sense to use SQL for these kinds of problems, or do I have a graph-based environment, or do I want to run things outside of the database, enabling me to use certain algorithms outside the database? So, sorry, did you want to say anything, Chris?
No, I think, as Dennis says, a poor graph traversal algorithm could be implemented using any technology, which is a great point. And
it is a very valid point.
Yeah.
Yes. And
I think this is one of these problems where the complexity stacks up very, very quickly. If you're working on any kind of real world data set, even just a few thousand rows, the number of possible edges quickly gets just simply unmanageable. So yeah, you need to understand what you're doing here. Okay, so question from Sven. Is there
and Sven's point is even more valid, I would say, because that was often the thing which I was interested in.
Yes.
Is there a real world scenario behind the question of a fully connected subgraph? Because in the real world, I usually see people looking for strongly connected components, and I'll come to that in a moment, rather than fully connected subgraphs. And particularly, as you were saying, give me all fully connected subgraphs. That's it may be an interesting exercise, but is that the real world challenge? It would actually be interesting if the author of the question would comment on that. Now, that aside, maybe we can just move on to the next this. So just to wrap up on the type of technology we would suggest to use for that purpose, like Oracle Spatial Graph here. Oracle Spatial Graph as a tool at the moment, as it is, as it stands at the moment, as an on-premise product, is geared towards data scientists and developers, meaning you shouldn't be afraid of scripting languages or accessing the data through APIs. That is what we currently offer. We have announced the availability of a Graph Cloud service, which will have a couple of tools making it a lot easier to work with these kinds of technologies. But that's not out yet. In any case, here what we have is APIs which are used to control the loading of the graph, the analysis of the graph, the pattern matching, and so forth, on the basis of Groovy, Python, JavaScript. You choose your favorite scripting language, and there's a couple of tools from our side going along with it.
Okay.
Right.
Should we?
Good. Yes. Maybe we can move on to the next slide, just so that we come to the answer of the question. And the key thing here, as you were saying, if you are looking for fully connected subgraphs, this would be, you say it could be slow, it would be slow. Once you go beyond a certain number of vertices, you just have an exponential growth of the number of subgraphs or clicks, as folks tend to say in the community. And usually what folks, if anything, what people would do is find the largest subgraph, the maximal click, and only the largest ones. There is an algorithm in the literature which you can find it as, if you know, a parallelizable variant, which is available. We have not implemented that. We could if somebody was threatening to throw large amounts of money at us. It's actually not so complicated because we have all the building blocks as part of the product. But what we would normally much rather do, or what people would much rather do usually on these kinds of data sets, is community detection. And then for that purpose, we would use what is known as strongly connected components rather than fully connected components. So if you move to the next slide.
If I go on.
Right? So strongly connected components, what does that mean? Strongly connected components, that's the maximal subset of vertices of the graph with the particular characteristic that every vertex in this connected component can be reachable from any other vertex in the component. And I've got a little sketch on the right-hand side here. I can see a community of 3, which is strongly connected. We have a community of 2 to the right, and the single lady on the lower left would also be a strongly connected component in its own right. Then we have 2 algorithms implemented, which we could use to run across the graph, and this would actually work on graphs of serious size. Right? I mean, customers of ours, what they would do is they would use like call data records, which usually have many, meaning millions, right? We would represent telco subscribers as vertices and calls between them as edges, and then you would run community detection, maybe to run targeted marketing or the like. This is what we could do with these algorithms, and they would run, as I said, not in the database, but in the in-memory analytics engine, using the specific storage structures which we have in that engine, and we would run them in parallel to the extent that they are parallelizable, such that they are actually pretty fast.
Okay.
Right, yes.
Yeah, okay. So this is just catching out the
Yes.
complete solution.
So that would be the usual approach to things. Now, as the question was, give us all the fully connected subgraphs, we would actually have to run this, or build a revision algorithm to do this, because we don't have that out of the box. We have, as I said, the bits and pieces. Like typically what you can do is, it's easy to find triangles in the graph, so you can just run over the entire graph and extract all triangles. And then based on that, you can pretty easily come up with an algorithm that would iterate over each triangle and then expand it by looking at the neighbors and check if that neighbor is already in the subgraph. If not, then it would check if all connections are in the subgraph. If not, discard it. If yes, they'll be included in the subgraph, and so forth. Right? So bottom line is, we don't have an algorithm out of the box that does this, but it is a very, very uncommon and pretty computationally intensive tool.
Yep, as we were saying, there could be a huge number of solutions here. So I think we've had some other comments come in, so let's just review these. So Visconti, email analysis for knowledge and communication. So I guess that's where you'd look at the strongly connected components. Is that kind of thing, you're looking who's been emailing who type thing?
Yeah, that'd be a good example. I mean, anyway, basically you represent many things as graphs, and looking at email communication is one. You're looking at influencers in an organization, not necessarily within strongly connected components, but other algorithms. That's not necessarily in line with European Workers' Council laws, but there you go.
Yes. Fair enough. Okay, so other comments here from Dennis. One of the examples which comes to mind is putting each and every path for a given graph into memory for further use. For instance, find the shortest way from X to Y, then seems to be indexing approach for graphs. I think that's a slightly different type of problem. That's like a sort of traveling salesman type problem, isn't it?
Yeah.
What's your take on that, Hans?
I agree. That is a different class of issue, I would say.
Yeah, I mean that's not to say you wouldn't want to do that. They're
We
definitely
can
use
do it.
cases.
I mean,
Yeah.
it's wonderful. It's a great fit with these technologies, right? Because we have things for different variants of shortest paths and things all pre-built into the product. So if that's what you want to do, sure. But
Yeah.
for the fully connected subgraphs topic, then there are probably easier approaches to selling.
Yeah. Okay. Some other comments. So an interesting one from Judith here. The real art of SQL is there exist possible constructs that only use SQL. Solutions that only use SQL constructs, short and easy understandable for any SQL developer. The Oracle Graph might or probably surely does offer more efficient solutions, but has a very high learning curve with many technologies and languages involved. For people who are not already Oracle spatial geeks, these technologies, however nice, remain somehow out of the mainstream for the large community of Oracle developers in comparison to the few ones using it for very specific projects. You got any comments there, Hans? Or?
It's actually interesting comments, Judith. So the approach we're trying to take here is to still use the underlying database, which is familiar to everybody here on the call, as the storage layer, and then potentially make it easy to interact with the graph once we have more tooling around it. At the moment, our focus has been on the core engine, providing pattern matching, providing the algorithms and so forth. But once we have the tooling with the graph cloud service, then it should actually be not too complicated. That's our design goal, to make it easy for like data warehouse developers to also include graph analytics in the analysis. And in fact, we already have a few of the algorithms like PageRank available in PGQL. So you can run these things straight down in the database. You don't need the in-memory analytics engine. You don't need to transfer the graph outside the database or anything. You run things straight on the database, and we have a PGQL to SQL converter, and I'll come to that in a second, which actually allows you to convert the relatively compact notation of a graph query into SQL, which will usually end up in a humongous SQL statement, but it runs against the database if you so wish. If the ILOUG program committee allows, I might actually come to the next ILOUG and talk about using the star schema in a graph analytics fashion. We've got a nice example of that one.
Oh, there you go. There's a great call. So I know, Judith, you're based in Israel, so if you want to see Hans show you how to do graph, then petition the committee to let him come. So, okay. So I think my take on this is, having seen some PGQL, I'm not going to claim to know it hugely well, but it feels SQL-like. Obviously it's got some of its own syntax, but as that matures, I think it'll become easier for developers familiar with SQL to switch to PGQL and as we mature that. And it's my understanding that ultimately the plan is to integrate PGQL into SQL in one day. So in fact, this will become native database technology. Anything you want to say on that, Hans? Or?
I mean, that's the midterm vision. In fact, we're working with the ANSI SQL committee on developing a integrated language which will provide problem graph query capabilities in SQL, just like we had Sparkle in SQL, which was a graph query type of thing inside of SQL.
Yeah. Okay. Cool. And comment about the Oracle Graph office hours. Judith says it's too high a level for beginners, so maybe we need some introductory graph sessions. I think that would be a good.
That's a valid point. And we actually, my colleague Albert was also on the call, and I were traveling around Europe at the moment, basically running workshops. And we have materials and so on. So anybody who's interested in a sort of more in-depth session on graph analytics, starting from scratch, feel free to reach out to us. We've been to a few places, but obviously we can't be everywhere at the same time.
Okay, so then. So I think we've covered this quite well, I think, and I think the main takeaway is if you want all the fully connected subgraphs, it doesn't really matter whether you're doing it in SQL or Graph or PGQL. It's almost certainly going to be slow, and some kind of offloading like Sven's done, where you're pre-computing stuff as you go along, is probably the only way this is going to be feasible for a lot of situations. But unless someone is the person who posted these questions on the call, or someone else has got a real use case for it, it's probably unlikely you're actually going to do a complete, fully connected subgraph of an entire graph. So it's probably more of an academic exercise for most of us. So let's move on to the other problem I wanted to discuss, and hopefully we'll get through this one. And what this is, find the hierarchical mean is what I've called this. And this was another interesting problem. So we see we've got a hierarchy. So we start at the top and work our way down. And you see some of these nodes have numbers associated with them. So we can see 23's got the value 30, 25's got the value 70, and so on. And what we want to do is calculate the average of these values, but with a couple of tweaks. First up, what we're doing is you're calculating the average of your direct children. However, for the leaves, these things at the bottom, the average is 0. And then when we get to the level above that, it's the average of itself plus its direct children. So we can see 22 has got 3 children, so we need to add up all these values and divide by 4, because there are 4 nodes in this little subtree. And if we go over 27 here, it has the value 55, so we need to add it to that to calculate the mean of those. So we've got these 2 mean values here. Now, when we move up to the next levels, then we are only considering the average of its children, not itself. Now, I'm a bit skeptical about this requirement for a couple of reasons. We are calculating averages of averages, which is, in my experience, is almost always the wrong thing to do. But I'll take it that actually this is genuinely the real need that the person's trying to solve here. But also we've got this little quirk where it's not always the average of its children. The one that's the leaf just above the leaves, it's itself plus its children. Everything else, it's just its children. So as we move up, we can see 26 and 21 only consider their children, 20 only considers 26 and 21, and so on. And 19 just has the same value as 20 because it's only got 1 child. So we're working our way, we built our hierarchy and we're working our way back up with this. Now, and in order to solve this again, we had some great solutions, but we made some simplifying assumptions. First up, all the leaves are at depth 5. So if we go back up here, in the generic tree, we could have a node 30 or 31 over here, which is a direct child of 19, and it's a leaf. That makes this whole average of averages, just the leaf thing, rather complicated to consider. So for the purposes of this, we're going to assume that's not a problem and that all the leaves are at depth 5. Solutions will need to be tweaked to take that into account, as that is not the situation. And that the additional values, so we can see we've got these 65, 75, they only appear on the bottom 2 levels of the tree. So the root has no value and so on. So there are a couple of simplifying assumptions. Whether these are true or just happen to be in the data that the customer sent us, we don't know. Okay. So how do we solve this? Well, basic solution is we walk down the tree and then you walk back up again, right? So you build the tree using recursive with or connect by, and then you walk back up it using, again, you could use recursive with, or you could use model clause. And one of the key things that can really help you with this is you are trying to calculate the average of nodes with the same parent. So that helps you identify which nodes you're actually combining together to actually do your average. And again, we're going to jump. We've got quite a few examples over on Live SQL, so hopefully it's this one. So we've got a whole bunch of data here to set this up. We can see setting it up, and this is the output we're looking for. Now, I'm going to whiz through these quite quickly because these are a bit more involved, and actually sitting here and stepping through them line by line is probably going to be a bit painful for all of us. So I'm just going to shout out to the people who've supplied these solutions and give my take on the very high overview of them. And if you've got any comments, you can follow them up. And you want to play more, just search for them and you can check them out afterwards. So let's see, this is, first up, we've just got the basic tree, building the tree itself. And then first thing I want to show is the solution from Udis, who uses pipeline table functions to do this calculation. So rather than doing it just in pure SQL, build a PL SQL package, which is a table function, so it's generating data, working through the data set, and doing this calculation. And you can see collecting the whole tree and then spitting it back out again. And again, it's a bit much to just kind of walk through all these individual bits, but the key point is we're looking, if it's a leaf, don't, give it nothing. If it's not, then work our way back up the tree. And as we can see, or hopefully we can see, we're getting exactly the data we're looking for. Another solution, another solution from Stu, who uses the model clause to put this all together. So we build up our tree with connect by, or however you want to do it to start with, and he uses the lovely model clause to do it. And then I notice this matrix key F is the parent of the current row, or the current node. And by putting this in a dimension, so the reference, how we access each thing in the model clause, we can then easily sum up all the rows for that same parent. So that's kind of what's going on in this little bit here. We're saying find the sum of everything, all the nodes at the next depth in the tree with the same parent, and any just means any of them. So again, this requires knowing the model clause to really fully understand it. But the key point here is we can reference what the parent is and use that in the model that we're building to kind of link those nodes together. Okay, and finally, we have got a complete tree walking one, recursive with. So we build the tree once and then walk back up again. So this is built by Matthias, so I see you there. So well done to you all. Thanks for providing the solutions, and we can see this also builds these. So rather than walk through them all, I recommend you have a look, think about how they work, see whether they provide what they want to do. So we've got some comments come in from Udis. I think my model, or my PL SQL solution can be transposed to a model clause solution, but one that applies rules node by node rather than level by level. Thus, there is no need that all branches have the same depth. So that's a good point. I mean, we probably can generalize some of these solutions, and some of them probably may well work general in case. Well, there's still just the general problem if we've got the root and that has a leaf connected to it, how do we actually calculate the average? As it stands, it's kind of undefined what that value should really be. And that's something for the person, the customer who asked this question to clarify whether that's even possible, and if it is possible, what should even happen there. So there's still some things that aren't fully defined, even if we've got different depths of tree available. Comment from Sven. I think for many types of questions that can be solved by SQL but need multiple hierarchical queries or other complex constructs, PSQL, or I guess you mean PGQL, might offer comparable solutions in terms of speed and maintainability hierarchical. So that's a great point. So Matthias, I see you put your video on. Did you want to say something? You want to talk about your solution at all, or if you? It's fine if you do. If you don't, don't worry. No, no, not in person. That's fine. So yes, that's a great comment, Sven, and that kind of leads us into the next thing that we are going to discuss. So again, Hans has got some thoughts on how to do this using graph technologies. So we'll bring us back over to the
to the
slide.
slides, yes.
Yes.
So as I mentioned already, as part of the graph offering we have, there's two things you can do. One is what I explained in the previous section, which is computational graph analysis using the algorithms which are part of the package. The other thing is we have a query language, which is kind of SQL-like, which you can use for the purpose of pattern matching. And looking at the problem, it did look like a typical PGQL type of thing. Just to give you an idea of what it looks like using PGQL, it is similar to SQL in that it has the typical select from where structure, and you have all the grouping and count and average and sorting and so forth. But in order to be able to do pattern matching, we also have an additional clause, which is the match clause, and potentially also paths, just like you would have in SQL. Like you could define a path like here, a path connects, which basically describes a pattern which you can then use a match clause, potentially even in a repetitive form, and then using this property graph query language, we thought, well, it can't be too complicated to actually do this hierarchical mean. So if you move to the next slide,
There we go.
we have this possibility of, as I said, defining a path, and if you have a path, you can specify to which depth you want to use it. So you can have it from 0 to an arbitrary number of recursions, or you can have it from 1 to 2 or 3 to 5 or whatever. And here in this case, we thought, okay, we have this this path with the clean start, which basically gives us reachability, meaning we could use that to find all groups of child vertices to a given vertex, and that would even touch every vertex only once. And the clean start in this case even gives us the possibility to match the to do the match 0 times, meaning we would even reach the leaf nodes, which you were explaining previously. So I thought, okay, well, it was actually my colleague Oscar van West, who's our lead developer on PGQL, who came up with this very compact statement for the hierarchical mean, which you can see on the right-hand side. Right? It basically has a select clause, which does a sum over the count, built on top of this this hierarchy defined by the has child path with the appropriate grouping. But looking at it more closely, you'll pretty quickly see that's wrong. Unfortunately, it's wrong. It is very compact. You can write with very compact PGQL statements doing fairly comprehensive analytics on either hierarchical or even cyclical graphs and so forth. But here in this case, it didn't help. So if you click once more, Chris, it just turned out that it is not the right kind of approach. We can solve this by means of scripting. We will have an algorithm API, so you can create your own algorithm, which is something we did not have exposed so far, which is due out in the next release. And based on that, using the built-ins we have, you can relatively easily create a script that does this. And if you're interested, we can have the script. So anybody who seriously wants to do this, I'll be happy to share that. But again, it is not something we could really do out of the box.
Okay. No, thanks, Hans. So I think that's kind of all we really had kind of prepared. So, and you've got a whole bunch of resources for anyone who wants to know more about this, haven't you?
Yes, so if you find graph analytics interesting, like Gartner, for example, finds it very interesting for anyone working on analytics at the moment, we do have, well, there's the usual, OTN page, the product page. We have tutorials. We have a quick start kit. If you want to get started, feel free to either DM me on Twitter or reach out to me on hans.feeman@oracle.com. I will be happy to work with you if you have a real world graph situation, or come to one of the upcoming user conferences. I just had my application to the DOA conference accepted, except that will be in German, so I might give you a hard time. But I'm coming to other places for that as well.
Okay, so if we just pop back, so Sven's asking, does this solution consider the average of average issue?
It's just not correct, right? It was just a first cut where Oscar said, no, it's got to be something like this. But looking at it more closely, it is not as trivial as this. So, really creating a simple PGQL statement works for other kinds of purposes very nicely, but in this case, it is not the correct solution. I should have actually crossed it out here just so that I don't create the impression that the PGQL statement is actually as simple as this.
Yeah, but I think it does show that you can walk the tree very easily within PGQL. So there are a lot of tree traversal problems, isn't there, where you can see that's pretty straightforward to do. There's a bit of syntax to get your head around, but
right. But it's not so different from SQL after all. And the only thing you need to get used to is the match clause. And if you look at it, I mean, I didn't explain that properly in the previous slide, but if you look at anything in round brackets is associated with vertices. Anything in either square brackets is related to edges, or in this case with the dashes, sorry, with the slashes. These are paths. It's not so complicated, and it is very visual, right? So it is relatively easy to comprehend. And other graph query languages work in a similar manner. There are more of these, and we're currently working on standardization as well.
Okay, cool. So we had a question come in. There's always the interesting cost question from Daniel. Is there a part in the graph and spatial option that's free if running Enterprise Edition?
If you want to use that for free, XE is actually what you would want to use. The graph capabilities, unlike the spatial piece where we have the basic, sort of the core features included in every edition of the database, the graph capabilities are actually only included in the option. So if you want to use that for free, the suggestion would be to use XE. Or there is also a lower cost offering on the Big Data platform. So there's a product called Oracle Big Data Spatial Graph, which has the same analytics engine, except it doesn't use the database for storage, but it uses either Oracle NoSQL or HBase. And that comes at a different price point.
Okay. So thanks for clarifying that, Hans. So we're getting close to the hour, so I've just got a general question for the people still on the call. Is this graph stuff interesting? Do people want to have like a 101 or a PGQL for SQL developers type session? If you find that useful, say yes, or there's little yes/no buttons on the participant screen, because I'd be curious to see if people who wants to know more about this. Okay, so thanks. No. Yeah, so if you, it's of interest, but nothing we use currently. Spatial and graph office hours, yeah, sounds good. It's okay, so is graph and semantic RDF the same thing?
That's a very valid question from Sven here. So if you talk about the graph in the sense of the licensing bundle, then we have different graphs in support for different graphs in the spatial and graph offering. We initially had graphs like for spatial technologies where you would have utility networks, road networks, and so on, which also constitute graphs. So we have a network data model, which is a graph. We have the RDF semantic graph. We've had that since 10G release 2. That is also still there. But here, the property graph capabilities are a completely generic graph implementation that is different from the semantic RDF graph. It uses different storage structure, it uses different bits and pieces, but it is a different part of the license bundle. But thanks for the question, because that helps me to clarify the different graph bits and pieces we have in our work.
Okay, cool. Okay, so thanks for clarifying, Hans. I think we're kind of on the hour, so I think we'll wrap it up. So just thanks to all of you who supplied solutions to the SQL problem. I think this was quite fun to see what people provided. If you like the kind of format of solve a problem, let me know, and we'll see if we can run more of these in the future. Also see if maybe there's some other problems which SQL may not be the perfect language for, or there's other languages which may have different strengths and different weaknesses. So I think that's good to recap. And I think also it's worth, for both these problems, it's worth us really understanding why people are actually trying to do this, particularly the fully connected subgraphs. It's just like, what's the real world use case for this? So I think it's always good to understand some background as well. So if you've got questions, if you can provide that information, then it also helps us perhaps guide you to a more appropriate solution, which is almost certainly going to be simpler to implement. Okay, so with that, I think to say thank you, Hans.
Well, thank you, Chris. It's been a pleasure here. And we did this, as I said, kind of at half, and I really enjoyed the joint session, so thanks for the opportunity.
Yeah, no worries. And thank you all, and I will see you all in the next session in a few weeks. Okay, cheerio all.